All right, it should be good. All right, so hello everybody. This is the next BCI-NE webinar at the University of Essex. And today we have the great pleasure to host Professor Calogero Maria Oddo. Let me give you a few more details before we start about the talk and about the speaker. So the talk we'll discuss is titled Touch Science and Engineering for Bionic Prostheses and Collaborative Robotics. The talk will discuss selected case studies of technologies developed for endowing robots and wearables with artificial tactile sensors distributed over large areas and to deliver tactile feedback, from bionic limb prostheses up to the metaverse. A first case study proposed is with the piezoresistive MEMS sensors applied to bionic hand prostheses to restore rich tactile skills such as texture discrimination in upper limb amputees. Selected achievements are shown in the talk, discussing the application of tactile sensing technologies in a gripper able to manipulate fragile and deformable objects in collaboration with NASA-JPL, enabled by combining FEM and machine learning, or for sensorizing the full area of an anthropomorphic robotic arm featured on the cover of Nature Machine Intelligence. Particularly, endowing robotic arms with large sensorized skins allows the implementation of smart collaborative policies, such as safe interaction and programming by demonstration, that can be deployed in the factories of the future. Finally, ongoing research directions of large area eSkins and neuromorphic touch sensing will be discussed also in the perspective of sustainable NeuroAI. And a short bio of our speaker. Calogero Maria Oddo has a PhD in biorobotics from Sant'Anna School of Advanced Studies in Pisa, Italy, MC, Master and Bachelor in Electronic Engineering from the University of Pisa, first and second level degrees in Industrial and Information Engineering as an honors college student of SSA of the same institution, all with honors. He is Associate Professor of Bioengineering. He holds the National Scientific Qualification to be appointed as full professor, and he coordinates the Neurorobotic Touch Laboratory at the Biorobotics Institute of the University of Pisa. He has over 130 published studies and several patents, and a track record of integrating biorobotics, neuroscience, and industrial applications with core of research interest in touch science and engineering. He has more than 6,300 citations and 36 H index in Scopus, and he serves as member of the editorial board of scientific journals such as Scientific Reports, edited by Springer Nature, and the International Journal of Robotics Research. He has a growing portfolio of successful research grants with scientific responsibilities within the European Union and national projects in Italy and industrial contracts. In 2023, he received the Feltrinelli Prize for Young Investigators in Bioengineering from the Accademia Nazionale dei Lincei, I hope my Italian is good enough, where he has leadership responsibilities as Vice Director of the Interdisciplinary Center of Young Scholars. And without further delay, Calogero, please, the floor is yours. Thank you.
So thank you, Simis, for the kind invitation. Today I will talk about touch. Touch that is nowadays a fundamental dimension of the evolution of sensing technologies, while in the past a lot of attention was dedicated to vision and audition, particularly vision for robotics. Now we are in the era of touch. We are in the era of touch. We are seeing this because humanoids that are being widely adopted in a few years. There are a lot of forecasts in this respect, and this technology will be more and more strategic. Before that, before entering into the details of touch sensing, let me quickly frame it in the context of sensory neurophysiology and sensory technology. We know that there are common features among senses that you can find in books texts such as the Candle for physiology. A stimulus, a sensory stimulus, is basically delivered and elaborated by our sensory organs and brain by means of three steps: the physical chemical stimulus that is administered to the end organ, and then a set of events that transform the stimulus into pulses, neural pulses, and then a response to this signal in the form of a perception of conscious experience of sensation. So it can be even movement at the end, the response. And this is common among all senses. The taxonomy of senses in the Aristotelic manner is organized in 5 senses: vision, audition, and touch, olfaction, and taste. And 3 of those senses are so-called physical senses, 2 are chemical senses. The reason why of this category is that the end organ in transducing the signal deals with a physical phenomena or with chemical phenomena. At the end, once that the information enters into the body, everything becomes, say, chemical, because there are electrochemical reactions of the neural pathways that bring information from periphery to the center and back. But the end organ is characterized to be physical, as it transduces a physical signal, like electromagnetic wave of vision, or audition is a pressure wave, or touch is another pressure wave, or chemical signal for olfaction and taste. It is fantastic to see sensory neuroscience, to understand how senses elaborate information, how human senses elaborate information. And the human senses are extremely elegant in the optimality of their organization. This is particularly true if, as an example, you look at the cochlea. That is probably one of the most elegant descriptions of the functioning of human sense. The cochlea basically does in hardware a Fourier decomposition in real time of the signal, because depending on the tone, depending on the frequency of the signal, we see it here. So different resonant frequencies of each site.
Just about a kind of STEM type funding opportunity.
Sorry, Vito, please mute.
Okay, thank you. The different site of the cochlea resonate at a different frequency, and therefore, if you have a distributed set of receptors over the cochlea, then they decompose the sound in real time into their frequency constituents. And this is very much optimized from the point of view of the processing, because we have basically a Fourier transform thanks to the mechanical resonance of that membrane, that it is the basilar membrane. This was recognized with a Nobel Award to George von Beckes in 1961 for the description of the mechanics of the inner ear that you can find here. There are other Nobel Awards which were given in the years to sensory neurophysiology, particularly from dioptrics of the eye up to cortical phenomena, but up to recent times, the scientific understanding and also recognition in terms of Nobel laureates has been limited, let's say, quote unquote, to vision and audition. Or recently, let's say 20 years ago, on chemical senses as well, with Axel and Bach Nobel Award. This understanding of sensory neurophysiology is leading, it is clear that it is leading to development of technology that are developed, also enabled by the neurophysiological understanding of the human senses. As an example, if you open the properties of the audio card of your computer, it will be likely that your computer has a 44 kilohertz sampling frequency. For high fidelity card, you reach up to 80, 90 kilohertz. Then there are professional for more than 100, like 200 kilo, 180 kilohertz. but these are very professional systems and very high cost. But typically, consumer products have a sampling frequency in the order of 44 or even slightly less than 19 kilohertz. This is a clear application of Nyquist principle of sampling principle for digitalizing data applied to the fact that we know that in human neurophysiology, young, healthy individuals have capability to perceive up to 20 kilohertz. So slightly more than twice that frequency is the sampling of our audio card. So, I mean, this is just an example, but the key message here is that there will be no MP3, no JPEG, no video audio compression strategy, no devices like video camera, photo camera, audio recording or reproduction systems that is capable to record and reproduce video and audio data without the understanding of sensory neurophysiology related to the senses. The sense of touch has been lagging behind the other senses for historical reasons. Probably priority in the research directions has been given more to vision for several reasons that can be also understandable. However, now we are entering the era of touch. We are entering into the era of machines that should guarantee capability to have a physical interaction between human and machines, between machine and machines, machine environments, and so on. This is clear if we look at collaborative robots, wearable robots, surgical robots, implantable robots. In all such machines, there is a need for a sense of touch to allow the machines to act and interact physically with humans and the environment. And to do that, we need understanding and we need technology. From the understanding viewpoint, from the sensory neurophysiology viewpoint, the recent year has been spectacular for scientists that do research in the field, like myself, doing research in touch. Also, thanks to the recognition that was given to David Julius and Arden Patapushan for the discoveries about the principles of transduction, the peripheral principle at molecular level to transduce information of temperature and mechanical sensation. David Julius was awarded the Nobel Prize for his discoveries about temperature sensing, particularly the role of capsaicin, of menthol. There are chemicals that are useful to used to transduce a sense of hot or cold touch. By the way, think to the fact that capsaicin is present also in spicy food. When you eat spicy food, you feel hot in your tongue. This is clearly a multisensory integration because the capsaicin is in common between spicy food, but also it mediates thermosensation for high temperature. So it is clear that there is also a multisensory integration in the brain that is happening between different sensory modalities. Patapushan and colleagues, but he was awarded the Nobel Prize, characterized the piezo channels, and the piezo has a Greek origin that recalls the concept of force or pressure, that are channels that deforming, open, and change the permeability of the membrane of mechanoreceptors, allowing ions to flow in and out, and therefore altering the membrane potential, and so that an action potential should be released to compensate, and that action potential flows up to the brain to give rise to perception. By the way, it's very nice if you go the social media of Arden Patapushan, very active in social media. When he was awarded the Nobel Prize, this is a fantastic post that Professor Patapushan did. when he received the Nobel Prize, because he received a lot of perks, like presents that colleagues, friends sent him for celebrating his Nobel Award. He received also a Tabasco set. So it's very nice what the post that he made. More Nobel Prize perks. Thank you, Tabasco, for the gift. Actually, it would be more appropriate for David Julius, but I'm keeping them. Because the reason why he's saying this is because, as you can see here, capsaicin is typical of pepper and spicy food, and therefore he was saying that his colleague would have deserved the Tabasco present, not him. Going back to touch and to particularly mechanical sense of touch, our approach in our group is to get inspired by human neurophysiology, but also to contribute to the understanding, to human neurophysiology understanding by having studies of the human sense of touch with several methods, with administration of stimuli, recording of biosignals, and also perceptual recordings, human psychophysical methods to characterize how humans perceive tactile stimulation, so that we can get design criteria for our tactile sensors to be bio-inspired. And when we reconnect to the prosthesis, our tactile sensors, we can achieve by inspiration on one side, so that our prosthetic systems could straightforwardly reproduce the human sense of touch when connected by means of neural interfaces, but also contribute to the scientific understanding. So this is a virtuous circle between science and engineering, discovery and invention, that has also translational directions in industry, so collaborative robotics, or medical application, including wearables, implantables, and so on. I will talk about this part later, about particularly this paper that was featured on the cover of Nature Machine Intelligence a couple of years ago. Remaining in science, an important technique that has been used historically is microneurography. This was invented by Åke Wallbo and Carl Erik Agbart in the 60s in Sweden. It's a technique consisting in the percutaneous insertion of needle electrodes through the skin, like acupuncture, with a very sharp and thin tungsten electrode that is made in contact with a single afferent fiber, so that when the electrode enters into the nerve, this contact can be used to acquire signal, electrophysiological signal from the afferent pathways and build models. You can see this clearly by means of these recordings that we're making in Pisa, because now we have founded recently a laboratory of microneurography and microneurostimulation in Pisa. This took several years to build this lab with a Faraday cage and to train the personnel to have ethics approval. But now we have this ongoing experiment that are spectacular. You can see this quality of signals here, top right, how is spectacular the quality of spikes that we are recording from the peripheral nervous system to create models that correlate the stimulus administered to the skin to the firing activity of the nerve. And this is allowing us to have first-hand recordings of human mechanoreceptor activities, so that we can build models of mechanoreceptors that inform the development of our artificial sensors. We also are developing open science tools. So if you look at the GitHub of my lab, if you search New Robotic Touch Lab in GitHub, or you look through this QR code, you can find a series of open access tools for the scientific community to use for, as an example, elaborating neural data and recordings from electrophysiological data, or for developing biomimetic artificial tactile sensors. And this is the kind of models that we are building. So having a characterization of human activity while we are recording electrophysiological data while applying a stimuli to the skin and characterizing the correlation between the stimulus applied and the electrophysiological activity in the nerves, then we are building models of activity of first-order neurons, but also cortical activity or intermediate layers in the human somatosensory connectome that is allowing us, and this will be the next topic that we'll go through in my talk, is allowing us to develop bio-inspired spiking artificial tactile sensors that can be usable in prosthetics, but also in neurorobotics. To give a minimal of common ground, but I guess everybody knows about touch neurophysiology, let me recall that there are a number of families of human receptors that are in our skin. Much more than the four, they are in number more than those four families of receptors that are represented in this slide, but let's say some of the most important families of receptors are those four: Meissner, Merkel, Pacinian, and Ruffinian corpuscles. The characteristics is that they are fast adapting or slowly adapting, or type 1 and type 2. What is the point? Type 1 or type 2 means that the receptor is, for type 1, close to the surface, you see in this case, or for type 2 is deeply located in the skin. This affects the receptive field primarily. So when you have a type 1 receptors, they have a very narrow and sharp receptive field. For type 2 receptors, since they're deep in the skin, the borders, as you see here, are less sharp, are more obscure, but the receptive field is larger. Instead, the other property is their temporal adaptation. So you see, for fast adapting or slowly adapting, basically slowly adapting have sustained response to sustained indentation. So if you apply a stimulus that remains static, they adapt, but they continue firing. While for fast adapting receptors, you have a firing only during the transient. Of course, this is a didactic simplification, but it's quite useful to create taxonomy of tactile receptors. The connectomics, so from the peripheral receptors that are, let's say, those four families and others, goes to the dorsal root ganglion where there is the first order neurons, then a cunate nucleus at the brain stem, still ipsilateral, then it crosses the midline, so it goes contralateral with a third synapse in the thalamus, and then in the primary somatosensory cortex on the contralateral side. So this is the connectomics, and the touch is very important because there are several studies, as in this video you are seeing, in which they demonstrate that without the sense of touch, we are not capable to carry out even a simple task such as turning on a flame and managing objects. So if we anesthetize the sense of touch, we lost this capability. This part, so the remaining part of the talk will be divided in two subparts. First, let's say 15 or 10 minutes in bionics, the remaining 10 minutes in collaborative robotics. I was saying that the understanding of human neurophysiology is informing our capability to develop touch sensors. And you see, we are getting inspired not only by the morphology, but also the fingers, as you see in this figure, but also the density of receptors and their positioning. So having a density that resembles the density of human mechanoreceptors, but particularly we're getting inspired by the signaling of receptors. This is a typical microneurographic recording in which from tactile receptors, and you see that there are those spikes that are the characteristics signals of neuronal signaling that instead are not present in normal output of MEMS sensors that you integrate into robotic hand. Those features, vibratory features, however, if you have a spectral analysis, you see this peak. The same peak that you find in tactile data, you find with the same stimuli in human data, in human mechanoreceptor data. So the question is whether we can transform the sensor output into spike-like data to be used for feedback, for triggering, as an example, in neurostimulator for neuroprosthetics. There are models that are capable to do that, so to transform a non-spiking signal into a spiking signal. Several models, including the so complex Hodgkin Huxley, from the very, very low complexity integrate and fire. A model that is in between complexity of Hodgkin Huxley and the simplicity of integrate and fire is the EasyQH artificial spiking neuron model. This model allows to emulate a variety of neuron families in response to a non-spiking input, transforming the non-spiking into spiking data. This is possible to be implemented in real time by integrating those differential equations of the EasyQH model with a simple method like Euler method on a microcontroller or on a digital machine. We can convert the output of the sensors into spike data that then can be used to trigger the neurostimulator to deliver tactile feedback. And you can see, while previously I was showing vibrations from the sensor output in the form of normal output of the sensors, here you can see instead the pattern of spike. This is so-called the raster plot. This is a pattern of spikes that is produced by our tactile sensors converted with the output converted by means of the artificial spiking neuron model. And the characteristics of this pattern of spikes is that replica of the experiment with the same stimulus, let me make a zoom here. You see, this is as an example with glass stimulus. Replica of experiment with the same stimulus are quite reproducible. Then if you change the stimulus, like from glass to paper, then you see that the pattern, again, is self-similar with the same stimulus, but if you look one stimulus with the other, or another and so on, different stimuli have characteristics pattern. So we demonstrated in several studies that with AI, with machine learning methods, you can use this pattern of spikes to decode the identity of the tactile stimulus. But in a series of studies that we have done in the years, we also demonstrated that it is possible to use the spikes produced by our neuromorphic tactile sensors to trigger the neurostimulator and to give a feedback to humans to be capable to integrate tactile sense in person that lost the limb. And this is the experiment we have published in some papers, including this paper that is highly cited, published in eLife 10 years ago, in which we demonstrated with this transradial amputee, as also confirmed by the amputee at the end of the experiment. This is a paper that we had done in collaboration with Professor Silvestro Mecera, Professor Rossini, and colleagues and friends such as Stanislas Popovic, Alberto Mazzoni, Giacomo Spiegler, and other collaborators. We demonstrated the capability to restore textural features, gratings, textural features of gratings, or textural features also of naturalistic tactile stimuli, as in this follow-up paper that we published again with Silvestro Mecera, Alberto Mazzoni, also Giacomo Valle was in the team, in the capability to recognize tactile stimuli even from a rich set of stimuli by means of neurostimulation in the amputee. So the amputee integrated in his or her sensorimotor scheme the tactile feedback delivered by means of the implanted electrode, transduced by our tactile sensors with a spiking model in between. And the spiking model was capable to induce the perception in a very natural manner. So in a few minutes, the amputee was capable to recognize those materials and to perceive their characteristics. This concludes the part for bionics. Let me switch to the second part of the talk related to application in neurorobotics, humanoids, etc., to introduce you a concept. Neuromorphic representations, for sure, that are those spike-based representations, for sure, are needed if you want to have a dialogue with the human nervous system. So if you want your tactile sensor to be reconnected to the nerves and restore the missing abilities in an amputee, clearly you have to respect the language of the nervous system. You need to use the same language. So when you administer the stimulus, you should use a pattern of stimulation that is similar to the pattern that we have in human physiology as characterized by means of microneurography. However, this technically has another side effect, positive side effect, that is the fact that if you sample a continuous waveform and if you represent in normal way this waveform will have, if you sample at 400 Hertz, will have several kilobytes of weight if you want to store this waveform. If you convert it into spike, and if the spikes are capable to represent salient information, this will allow compressing the weight of your data. So the weight of your data represented by means of spikes, since you just have to store the timestamp of the spike, allows to tremendously goes down in terms of dimensionality. So you can scale even 3 orders of magnitude of signal weight. And this allows, in technical application, not necessarily to save storage, but to integrate larger sensor networks, because a problem today is that the sensor networks are not so dense. Instead, with this representation of information, representation remains salient, but also lightweight, so that you can integrate a huge sensor networks. And we are going in this direction, not only for neuroprosthetics that I mentioned before, but also to go in telepresence for a variety of applications, including telepalpation, humanoid robotics, medical applications, etc., etc. Among the several studies that we have made using technologies such as tactile sensors, then we used in human colonoscopy as an example to sensorize the colonoscopy with tactile sensors, but also tactile sensors plus ultrasound data for digital pathology. So for monitoring the presence of nodules within histological samples and help medical doctors to do medical diagnosis. But in the rest of the talk, I will focus on a technology that is fiber Bragg gratings, that is a fantastic technology that is been nominated in memory of William and Lawrence Bragg, father and son, that got the Nobel Prize about 100 years ago for the discoveries in crystallography and, let's say, using resonance with X-rays, in their case, for analysis of crystals of matter. And the same principle, the resonance with light, can be used to build the sensors. To build the sensors, because you see the back-reflected signal that if you illuminate an optical fiber, we've integrated those gratings, then the signal that goes back is proportional to the wavelength of each of those gratings. Then if you apply a strain to the fiber or to the material in which the fiber is integrated, those peak deform, those peak move, and therefore moving, they can be used as a transducer to sense tactile data. Tactile data that you can use in respiration, as an example, as in our activity when we are breathing, we have our mechanoreceptors distributed in our thoracic cage that are capable to give us information about our respiratory activity. And so we demonstrate in a series of studies that these sensors can be useful to recognize respiratory activity and follow the pattern of respiration and predict rate and flow of respiratory activity. Sorry for the blood here, but also in implantables. Technologies that are capable to monitor mechanical activity on the heart, in implantable neuroprosthesis for sensors integrated in the myocardial membrane, with these Bragg sensors integrated into polymeric materials that are sutured on the heart. But also, and this will conclude this stream in the remaining 10 minutes, in the humanoids. Humanoid robots, by integrating into the hands, or in general the limbs of the humanoids with those technology. Why this technology is very interesting for humanoids? Because it is optimized in terms of wiring. Because with just a single optical fiber, in a single optical fiber, you have the integration of a lot of transducers. So with a single optical fiber, it is like a nerve at the end, as we have the median nerve, as we have the ulnar nerve. In this case, with a single optical fiber, we can bring a lot of transducer delivered with information acquired via the optical fiber. And you can see the very nice result that we achieved. This is in a collaboration with the Jet Propulsion Lab of the American Space Agency of NASA, in which we demonstrated that our sensors were capable to integrate in this very rugged hand to be capable to gently manipulate even fragile or deformable objects. By the way, this is a very important milestone in robotics because current robotic hands are not capable to achieve the manipulation of the soft deformable object as our hands instead are capable to do. This, the intended application in this case was for civil protection. You can imagine in case of earthquake or fire and so on, a robot that can help rescue, search and rescue of people that should be to save their life. The final part, we show the application of tactile sensors in the development of collaborative robotics, particularly fiber grating, and also I will show how the application of neuromorphic solution can go in the direction of sustainability. So to allow those sensors to be sustainable from the viewpoint, as I was saying before, of the lightweightness of the data produced by the sensors, but also from the environmental sustainability, from the energetic footprint, or in general for the portability, because if they become with lower consumption thanks to spiking neuron model, this can be an asset that is very important for sustainability of AI solutions. The trend that we are looking now is the so-called collaborative robots, to allow robot to go out the cage. In the past industry, that is like industry for 3.0, but even 4.0, I mean, robots were closed in cages. You see here on the left that you have or the robot or the worker. In past robotics, you didn't have a shared workspace between humans and robots, because otherwise the human would have been at risk of their own life. Instead, in modern robotics, you have machines that share the workspace thanks to sensors. Thanks to sensors integrated, including proximity sensors, including tactile sensors that allow having interaction between the robot and the environment. The robot and the changing, evolving environment. This is what we demonstrated in this first paper in Nature Machine Intelligence that we published in 2022. First author was Massari, was the coordinator of the study. The title was a functional mimicry of Ruffini receptors. with fiberback gratings and deep neural network enable a bio-inspired large area tactile sensitive skin. This is very important, concept of Ruffini receptors. You see here, we got bio-inspired. This was not just engineering. This was engineering inspired by neurophysiology. So we studied the neurophysiology of touch, and then we tried to translate this neurophysiology into the morphology of the devices that we integrated into a large area polymeric skin to be capable to sense, and by means of the transduction operated by the photonic sensors plus machine learning, so neural networks, to be capable to localize the stimulus in a large area tactile skin and use this localization for controlling collaborative robots. So you can see in those videos on the left, the creation of a ground truth of calibration for neural networks. So here we had, you see, a calibrated load cell with the sensors of the skin, the position of the sensors that moved the skin to apply a stimulus to the skin that generated data set, by means of which we trained a multi-neuron, a multi-layer neural network to have an inference of contact of force and the contact location that you can see here. And on the right, you can see the application. I mean, in this case, it was just detection of a caressing of the robot, and the robot, when it was in contact, was just stopping. The evolutions of this study is some unpublished result that is going to be published soon on studying also the motion of tactile interaction, but also in going from traditional machine learning, as the previous paper that we published in Nature Machine Intelligence, in which we applied traditional machine learning methods to have inference of tactile quantities, moving instead to architecture-based processing with connectomics, with a connectome inspired to the so-called cunate nucleus, cunate neurons, so first order and second order neurons. And this is the follow-up study that we published a few months ago in August 2025 in a second paper in Nature Machine Intelligence, in which we demonstrated with the same skin, instead of using machine learning, we used the connectome. So we created a connectome of neurons that brought information, transformed the information from the lambda of the skin, so from the Bragg output, into spiking data of primary mechanoreceptors, and then a second order mechanoreceptors that you can see here, cunate, sorry, not mechanoreceptor, second order neurons, cunate neurons that received information from first order neurons, so from the mechanoreceptive neurons, to elaborate such data. But in this case, not with traditional AI, but with connectomics. So there was an architecture of flowing spiking data that was elaborated by a network of spiking neurons to be capable to recognize the localization of tactile stimulation and the intensity of tactile stimulation, not only in a single touch, but even in a multi-touch. So we performed even experiments including multi-point of contact so that the skin was capable to localize whether it was one or two stimuli, and similarly to the so-called two-point discrimination threshold experiment that have been done in humans. Nevertheless, and this will go to the conclusion of the talk, there is a question of sustainability. Nowadays, there are a lot of reports that raise attention to the sustainability of AI, on whether we will need a nuclear plant around big HPC farm, data centers that store data, that elaborate data, and so on. Possibly one solution could be to move some of those data centers maybe in space, since you can move the server and the HPC solution in space and do like on the moon, and do the training on neural networks on HPC solutions that are outside the heart. However, you want the inference to be implemented on the edge locally. And nowadays, there are technologies such as the N6 sensors produced by STMicroelectronics. Let me disclose, as I was saying at the beginning, that I have collaborations ongoing with STMicroelectronics. The first slide has a disclaimer with this, in which there is, as an example, now there are microcontrollers that integrate AI coprocessor, so that is capable to do inference on neural network on the edge. But we are going even more along this direction. So on the edge, rather than using traditional AI solutions such as, let's say, CNN, normal deep learning methods, or transformers, etc., so traditional, contemporary state-of-the-art, but traditional AI, we are going in the direction of brain-inspired AI. And in this paper that was published a few days ago in Nature Communications, you can find in my scholar profile, if you search for brain-inspired spiking architecture enables energy-constrained touch encoding. It was published a few weeks ago. We demonstrated in collaboration with my group, in a collaboration between my group and Professor Giacomo Indiveri from Institute of Neuroinformatics and STMicroelectronics with Giuseppe De Soli representing STMicroelectronics in this collaboration. We demonstrated that the use of a spiking chip can, on one side, achieve metrologically very, very good performance in recognizing the localization of the stimulus, even multi-touch, and the intensity of the stimulus. This was the PhD work of my PhD student, Andrea Ortone, but also to save energy. And so we are going in the direction of connectomics, brain-inspired, implemented in hardware with spiking neural network. And as the human brain is doing, because the human brain is processing data not with logics like if, then, else, not with a code. We don't have a software in our brain that elaborates data. We have an architecture. So it is the architecture between neurons, the architecture of neurons that we have in the brain or in between the body and the brain that elaborates in real time, live information that is ascending and decides the policy of control. And this is strategic to go in this direction because it can allow radically saving energy, as our brain is consuming a few tens of watt, not the kilo, mega, terabyte that are needed for computer up to a HPC facility. So to respect and get inspired by human connectomics, by human neurophysiology, can be enabler to go in the direction of radically new solutions, not only for prosthetics, that is the field from which our research stems, but also for humanoids of the future. And in fact, for this reason, we are collaborating even with companies that produce humanoids, and they want humanoids to be sensitive even to tactile sensation. Before concluding, let me just have a few consideration at higher level, by quoting Geoff Nicholson of 3M, the inventor post-it. It's very interesting, the definition he gave to research innovation. You may agree or not, but it's a nice definition. Not necessarily we can agree, we have to agree with this definition, but it's very interesting. So research is the transformation of money into knowledge. Innovation is the transformation of knowledge into money. What I'm trying to give evidence is that this can be part of a virtuous circle between research and innovation, between basic fundamental research and applied research, between The keywords of research are science, discovery, research. The keywords of innovation are technology, invention. Typically, the engineer invents, the scientist discovers, but in our field, there is a blend between those two lines, research, innovation, science, and technology transfer, science and engineering, discovery, and invention. And my forecast, in consideration of how things are evolving, is that the upcoming megatrend is physical AI, and a very important enabler for physical AI to take place, particularly in humanoid robotics, is the availability of touch with touch science and touch engineering. And I tried to give in this talk the idea that an integrated alliance between neurophysiology research and the translation into engineering can be strategic in order to allow machines to integrate rich tactile sensors and be able to act, interact, and also to substitute missing sensory motor abilities. I would like to thank my lab. It's composed by approximately 25 researchers plus master students. And nowadays, to keep a lab such as this, quite big like this, active, is very challenging, but it's also very stimulating. I'm open to any collaboration you may want to pursue, so feel free to contact me for collaborative initiative, research projects, and so on. It will be very, very interesting. And let me thank again Simis, Professor Perdidis for the kind invitation.
Thank you very much, Calogero, for this really interesting and also really, really broad in terms of, topics that you have touched upon talk. Are there any questions from the audience? Yes, Tassos, please go ahead.
I was clapping, but since you've given me the word, I do have a question.
Yeah, go.
I did have a question, Calogero. Hi. You showed in one of your slides that you had a participant who was discriminating between different textures based on tactile information virtually. But my understanding is they weren't able to tell the material, they were just able to discriminate the textures. Is that correct? So the question is, what does it take to get to the point where someone can say this is glass, this is, like actually feel the texture as they felt it before? What fills that gap?
Yeah. Thank you, Tassos, for the very nice question. That gives me the possibility to better explain the two experiments I presented. The first experiment, yes, you're totally right. It's three alternative force choice, actually, was the question. So the subject was asked whether he perceived the first or the second as coarser, or whether he perceived as the same. So at the end, what we did is to create a psychometric curve of rated perception. So depending on the difference in coarseness between the first and second stimulus, by changing the delta coarseness between the first and the second, we created this psychometric curve and characterized the psychometric curve of the human amputee stimulated with neurostimulation in comparison to the human physiological perception. With this first experiment, you can find this video as a supplementary material to the eLife paper. So it's online, is available online in the eLife website, in the journal website. If you look at the interview, so if you listen to the interview that he gave, at the end, what he declared that the stimulation that was administered by means of those spikes allowed him to perceive the stimulus such as in picture. So he could create a mental picture of the topography of the stimulus that allowed him to recognize clearly the roughness of the stimulus. But in that specific case, it was not the material. It was just the topography. But it was a first step. Then there was this follow-up study that we published in scientific reports in 2020, in which we used two models of receptors. And in this previously I had no time to focus. One model of slower acting type 1 and a model of type 2 receptors. And we demonstrated that with the model of type 2 receptors that are surface located, capable to recognize more in details the material characteristics, the subjects were capable to recognize not comparatively the stimuli, but in absolute recognizing them. So in this second study, the human amputees that tested the technology with a chronic implant on the median nerve were capable not only to say, okay, this is coarser than the first is coarser than the second, so comparatively, but in absolute terms, okay? So saying, okay, I'm touching wood, I'm touching Velcro, I'm touching rubber, and so on.
But
What is the limit?
was this a matter of training, or it felt like it did before, let's say, before
No, the strategy of stimulation was basically the same. Was a matter of stimulus. Previously, the experiment were just with gratings, while here the experiments were richer stimuli with naturalistic stimuli. Clearly on a constrained data set, not huge, so it was not 100 of stimuli. In this case, there are 6, but then the subject was asked to recognize the identity, not the reference of the stimuli, not to compare in comparative manner. The difference between this study and the one that was published 4 years before is because in this paper we had just 1 month of experimentation. This was the first human trial worldwide. This was probably the first trial worldwide of chronic implantation, but the ethics approval was just for 28 days. So it was an implantation and then a removal of the implantation. So we had very limited time. It's like when you have an astronaut, you need to have a lot of experiment running with the astronaut, and they have a timing, a Gantt chart of the experiment with a very, very hectic timing. Instead, this second that was no more the first human, but in this case, the previous study demonstrated feasibility. In this case, the implantation lasted longer, about 6 months. And so with this experimentation, we could perform a richer set of experiments, demonstrating that it's possible to go from roughness estimation with this forced choice protocol towards a richer perception as we demonstrated in this experimentation. I hope, Tassos, that I replied to your question. Of course, much more is needed, and possibly the next implant we will go in the direction that you were evoking with your question.
Thank you.
All right, thanks. I think we have some time for another quick question.
Sure.
Is there another question from the audience? Otherwise, I have one. All right, so I will go ahead with my question. In all these touch sensing experiments, you're stimulating the peripheral sensory neurons, right, in order to cause the sensation. Is there any evidence that we might be able to do something similar with non-invasive cortical stimulation, such as, that we can do with TDCS, TACS, and so on?
Well, there are studies of Sliman Besmaya, unfortunately passed away. Sliman suddenly, a couple of years ago, that demonstrate that with cortical but invasive stimulation, so with microstimulation on the cortical, it's possible to evoke rich perceptions. And this is maybe applicable not for amputees, because for amputees, I believe that to use cortical stimulation is not the best, because not only because of different invasiveness, but because you are not exploiting the computational properties of the afferent sensory pathways. I mean, if you stimulate the nerves at the level of the lesion, then you're exploiting the natural afferent, the computation and the natural afferents, the cunating,
and you have
thalamus, and
available
so on.
peripheral nerves. But there
Exactly,
are other
exactly.
pathologies, for
In other
instance,
pathology like
degenerative,
spinal cord
that you don't
lesion,
have.
yeah, like spinal cord lesions and other pathologies that instead do not have the channel working, and then you need to go at a higher level. In higher level, as I was mentioning, there were some pioneering studies by Sliman Besmaya and other groups that demonstrated, provided evidence of that capability. It's possibly another alternative to go in lower invasiveness. To my understanding, as an example, TMS stimulation, the drawback is that it requires large instrumentation with the magnets, with the electromagnets. So, I mean, probably it's not the best to bring when you are walking the street instrumentation like that around your head.
Yeah.
But maybe it could be electrocutaneous on the face. So there could be some non-invasive solution that could allow avoiding having a neural implant on the brain. So, of course, as more the neurotechnology is evolving, so if you're having electrode that can be surgically implanted and so on, then probably the invasive solution could be a good solution. However, non-invasive in some cases, like vibrotactile, electrotactile, and so on, can be the solution. Yes.
All right. Thank you very much. This was really exciting. I'm sure we're gonna open up some collaborations in the future.
Well,
for the moment, thank you very much, and I think we can stop here. Bye
thank you
bye.
for the very kind invitation. I was happy to be with you. Bye bye.
Bye.
Bye. Thank you.